Hello. It seems that not all the students understand the concept of statically indeterminate torsional problems. That's why I prepared these example problems with a little bit more examples. Okay, the problem was partially caused by the authors of the textbooks. They do not use different notations to explain internal torsional moment and the external torsional moment. Please make sure that in the case of actually loaded members, to indicate the external forces, we use the capital F, and to indicate the internal actual force, we use capital N to distinguish the external forces and the internal forces from each other. But in this chapter, we used both T, capital T, to represent torsional moment. Okay, so let's consider these example problems. Here we have an assembly of tube and bar, and they are attached to each other, and then they behave as a one piece. Okay, so in the textbook, they said we can decompose the behavior into two different problems because of using the principle of superposition. And the actual system is a superposition of those two example problems. Okay. This is given in the textbook, but I already explained you how to approach these problems using my diagram for the analysis. Okay, so let's consider the same problem using my diagram. Okay, again, the left-hand side is supported, and then the right-hand side is subjected to external torsional moment. Please make sure that this is very important to note that this is external torsional moment, okay? And the external torsional moment means in my diagram is here, the external force. And then because it is subject to the external torsional moment, maybe the right-hand side of this structure would be rotated. It experience the angle of twist. And because of this angle of twist, we have certain distribution of displacement here. For example, this is point B. And then make sure that this is homogeneous problem, the prismatic members. That's why the deformation is homogeneous. That's why to represent this angle of twist, we can use a straight line because this is homogeneous. Any gradient of angle of twist is constant for this problem. And then make sure that this is kind of displacement, okay? Displacement vector. And then this is elongation. The elongation, this is elongation measured, measured between point N and point B. Because the point A is equal to 0, point A is equal to 0, at displacement is equal to 0, the elongation is measured as pi B. And then let's consider the formula that we can use. This is a shortcut formula. Now here, look at this, that the torsional moment is equal to GIP divided by the length, and then the change of angle of twist between 2 points. Here, make sure that delta P is equal to PB here. Okay? So if you plug in this, and then we can obtain the torsional moment of bar and the torsional moment of tube separately. So make sure that here we have to use the polar moment of inertia for bar and the polar moment for tube separately. They are different. Then at the last time we want to check, at the last step we want to check the force equilibrium at the end point here. Okay, so according to the force equilibrium, so make sure that they are internal torsional moment, okay? But this guy is external and internal. But if you want to check the force equilibrium, so we actually, these three torsional moments follows the sign conventions defined in this way. All the torsional moment, sum of this, and then because we have to use double arrow, it should be equal to 0. Because these two guys are heading in the left-hand direction, that's why we have to use the minus sign here. And then torsional moment, the external torsional moment has the plus sign. So let's plug in the information of the torsional moment of the bar and torsional moment of tube into here individually. Then we can calculate the information of the angle of twist at point B. Okay, that's how we calculate the result of analysis. Okay, say let's consider second alternative here. It's given in the textbook, superposition principle. Okay, here we can imagine, actually this concept is given in textbook too, here. This is that concept. So we decompose the problem into tube and then bar here. Okay, so if, because of force equilibrium, make sure that the torsional moment is resisted by the system 1 here, and then torsional moment resisted by the system 2 must be equal to the external torsional moment, because this is force equilibrium. So I told you several times that, and although we use the term of force to explain the force equilibrium, the same equilibrium condition must be applied to the moment equilibrium too. So this is a torsional moment equilibrium. The external torsional moment should be equal to the external torsional moment carried by structure system 1, and then another torsional moment carried by structure system 2. So make sure that T2 is equal to external torsional moment minus the torsional moment resisted by the system on T1 here. Okay, this is the condition. Okay, so let's use our shortcut formula between the change of angle of twist and then apply the internal torsional moment. Then we can calculate the angle of twist at point B and the point B separately. Okay, this is what happened in individual system. And then we can add them up to obtain the actual torsional moment here. And then please make sure that these two structure systems, what I mean system 1 and system 2, they are in one piece. The one piece means there's no gap, okay? That means the angle of twist at point B of system 1 should be equal to angle of twist at point B at system 2. They are same. So instead of PB1 and the PB2, so we just want to use PB, okay? Okay, so if you plug in here and then using this force equilibrium, then we can obtain this expression. Okay, finally, if you rearrange all the equations, so we have the same answer here. So please compare the result with what we obtained in alternative 1. Using my diagram, I have same conclusion. Okay, let's consider another case. Okay, let's consider a little bit weird one. So instead of talking about separating here, so I want to cut here. Okay, I want to cut here in the middle. So because we cut in the middle, and then we have to apply another set of torsional moment. So coupled torsional moment, both sides, okay? All right, and then we apply the external force to only the system 1 here. And then in system 2, we apply the internal torsional moment only. Okay, so the actual system is the consequence of the superposition of these two structure systems. Then we can calculate the angle of twist of system 1 very easily using this formula, because in system 1, because the bar inside is cut, so it cannot resist and it cannot carry any force contributions. That's why we neglect its contributions. We only have the tube part, so we can calculate the angle of twist of system 1 very easily using the formula, the shortcut formula. So I told you that if you don't like to use shortcut, we can go into deep material point. But in the case of torsional problems, we have infinitely many points. That's why it is very difficult to handle all the material points at each time. That's why instead of handling all the material points, we use shortcut in this torsional problem. And then let's calculate the displacement, angle of twist here. Because this part it was not subjected to any load, that's why the angle of twist here should be equal to 0. So make sure that this is a displacement, not any change of angle of twist. Make sure that any change of angle of twist always depends on choice of coordinate system. Because we are using this coordinate system, we need to subtract any quantity from here, okay, to obtain the angle of twist. Okay, so how about here? because this is deformed as a rigid body. That means the angle of twist here should be equal to angle of twist here, because there is no internal torsional moment. Okay, it is same as the angle of twist calculated at point B. Okay, this is a very important point to understand. And how about let's consider point the system 2. In the case of system 2, we have internal torsional moment Tc as a loading condition. We applied the torsional moment here, and then this part is twisted. That's why its length is only half of the length of whole structure. And then we calculate the angle of twist at here. Okay, that's the meaning of this. So Pc minus. And then next step is we want to calculate the angle of twist here. Okay, so this is kind of serial system. So this bar is twisted, and then this tube is twisted. This is bar and tube. Make sure that the tube side is length is half, and then the bars, the tube bar side is length is of half of the original length, and tube side is length is equal to L. Okay, this is kind of serially coupled system. So we can calculate the angle of twist measured here very easily. Okay, and then let's consider compatibility. Make sure that this is one piece. Okay, one piece means there is no gap. No gap means eventually the angle of twist measured at point C little bit left hand side, and the angle of twist measured at point C little bit right hand side should be equal to each other. That means no gap. Okay, no gap. This is compatibility. And then to obtain this displacement, we have to superpose displacement from system 1 and system 2, and also vice versa, same here. And if we plug all that information that we calculated before, and then finally we have the same result. Okay, actually in this case calculation is a little bit more complicated, and please follow the lecture note that I uploaded today, and then you can find out the same, we can get the same conclusion. Okay, so whatever we do, we can get the same result. Okay, as long as you follow the procedure carefully. Okay, all right, see you next time.